Okay.
Yeah.
So
welcome to this week's string seminar. We have Vasilis Niarchos from the University of Crete. He's going to talk about 16.0 bootstrap with soft-Actor-Critic. Over to you, Vasilis. Thank you very much for being.
Thank you very much for the invitation. It's a pleasure to give this talk. So I want to talk about some recent and ongoing work that we've been doing with Kostis Papageorgakis in Queen Mary University in London, and also Gergely Cantor and Paul Richmond also in Queen Mary. First of all, so the talk is going to be based on a paper we posted a year ago, and also something that we posted very recently. Please keep in mind that what I'm going to discuss is very experimental, and we're basically trying to discover if, something new, but it's not completely clear yet what the possibilities are. Okay, so, okay. Doesn't go down. Okay, here it is. So the problem the general problem I'm interested in is quantum field theory, in particular the non-perturbative structure of quantum fields. We know that this structure is very rich, but poses a hard conceptual and computational problem. We have all these examples that we've, all these structures that we've uncovered over the years, like, for example, strong weak coupling dualities between quantum field theories, also strong weak coupling dualities between quantum field theories without gravity and theories with gravity and strings, which go under the general title of holography. Also, we have discovered by studying string theory many new exotic quantum field theories and relations between quantum field theories across different dimensions. But I think it's fair to say that the traditional tools, which are based on a Lagrangian or a path integral, are limited beyond perturbation theory. And we have some extra tools, for example, anomaly matching, or if you have extra symmetries like supersymmetry, you can use non-renormalization theorems, or the very nice tools of supersymmetric localization, or in some limits, like, for example, in planar limits, you can use integrability. But most of these tools have a limited scope. Even worse, there are many theories which we have discovered in string theory, which do not seem to admit a standard Lagrangian description. And one of these iconic examples is a 6D 2,0 superconformal field theory, which will also be the star of this talk. So if you have no path integral formulation, how do you compute anything? Clearly, we need to go beyond the traditional tools we have been using so far. So the general question that is sort of in my mind is there any other way to learn a quantum field theory? And I use the word learn here in purpose, having in mind all the recent progress, exciting progress that is happening in machine learning. We see every day around us machine learning algorithms being applied in all sorts of everyday problems. Machine learning algorithms can be trained externally, or so they could be supervised, or they could be unsupervised, and they learn on their own. They are trained on big data to recognize patterns, make decisions, and achieve goals. And in most of these cases, they ignore the microscopic rules of the game. For example, in Google Translate, Google Translate doesn't translate like a human translator that knows the microscopic grammar rules of both languages and then translates from one language to another. Basically doesn't know any grammar at all. But it has been trained to recognize patterns and make the translation. Not everybody greets this progress with excitement or with approval. For example, this is a picture here of a recent article in CNN from a couple of weeks ago, where some guy entered a digital picture contest where he used an AI to create paintings. And he won the contest. And then in social media, people, some people were reacting negatively, saying that this is not art. Anyway, so what interests me more is whether we can use this, if you want, this new approach or these kinds of these algorithms to say something new about formal problems, problems in mathematics or formal problems in physics. So two questions that I think are probably obvious are, could ML lead to a different perspective on what and how we compute in quantum field theory? Perhaps there will be a new synergy between analytics and numerics in formal problems. So you don't expect to put the computer on a formal problem and get a final answer by pressing a button. You expect to have a complicated, if you want, collaboration between analytic work and numeric work. One helps the other, and you get to a novel result. So these are the kinds of questions I'm interested in. And if we want to put such algorithms in work in quantum field theory, one obvious question to ask is quantum field theory a big data problem? Right? Because this is where these algorithms are excelling at the moment. And in an obvious way, if you want, the answer is yes. Quantum field theory is an infinite collection of quantum data. You have operators, you have all the correlation functions, local correlation functions that you can build out of it, and out of the operators. And you can ask in the formal space of all possible sets of quantum data, which is infinite dimensional, some answers are going to be consistent and correspond to a well-defined quantum field theory. Some answers are not. So can one search through this big space to identify consistent subsets, specific theories? Are there sufficiently constraining consistency conditions? And of course, technically, the problem is, how does one put the search on a computer? Obviously, these kinds of questions are not new. It's basically also what we have in mind when we discuss the conformal bootstrap or bootstrap approaches in general, or the axiomatic quantum field theory approach. So the question in this context is, can you find a particular context where the machine learning methods could be a useful new tool? So a context where things are, instead of taking the generic quantum field theory, which is a complicated, the most complicated situation, let's consider a more controlled situation, which is the situation of conformal field theories. So what I'm going to discuss is directly relevant for the conformal bootstrap approach. So I don't want to spend a lot of time reviewing conformal field theory. I believe in this audience I don't have to do that, but I want to set up the notation so that everybody knows what we are trying to do. So what we're interested in is a conformal field theory in generic dimensions in flat spacetime. And as you know well, the local structure of conformal field theory is characterized by a discrete set of data. So compared to a generic quantum field theory where correlation functions are complicated functions of the space-time insertions, in conformal field theory, there is only a discrete set of data, infinite, but discrete, that controls all the correlation functions, and you don't have to worry too much about the space-time dependence. So what are these data? You need to know what operators you have. In particular, you need to know the spectrum of conformal primaries, which are characterized by some charges, scaling dimensions, the spin, any other global charge that you have. And then you also need to know how you take two conformal primaries, you bring it together and make the operator product expansion. What are the operator product expansion coefficients? Or in other words, you need to know how to compute the 3-point function coefficients. Now, once you have this, then in principle, all endpoint functions can be extracted from the 2- and 3-point function coefficients, the above data, basically. So you can ask now, okay, so if one gives me a particular list of all these numbers, does it form a consistent answer? And it turns out that these data are not arbitrary. Unitarity constrains them. Crossing symmetry relations constrain them. So solving these consistency conditions, for example, the associativity of the OPE algebra, is precisely what the conformal bootstrap program is trying to do. Again, just to introduce the notation here, if we have a 4-point function of 4 operators, the idea is that we can take the OP in 2 different ways, either by bringing together 1 and 2, or 3 and 4, or on the right-hand side, 1 and 4, and 2 and 3. And on the left-hand side, for example, we bring 1 and 2 together, we fuse them, that creates an operator OK, and that operator OK runs here, and then you have the 3-point function coefficient here of OK with 3 and 4. And that gives you an expansion in intermediate conformal blocks or intermediate operators running here. Just to highlight the notation here, S here means that this is the S channel if you want, T is the T channel, and then you have the OP squared coefficients appearing in front of like one OP coefficient here and one OP coefficient here, so an OP squared coefficient. And then the space-time dependence, which is expressed in terms of two conformal invariant ratios defined in this way, and also expressed in terms of this complex variable Z and Z bar. This is the so-called conformal block, and the very nice thing is that this is completely fixed in a theory-independent way because using conformal symmetry. Okay, so if I take the left-hand side, say the right-hand side and put it on the left, then I have an equation of this form. It's linear in the OP squared coefficients, and then you have a function here, which basically you know, but it's a function, it's a highly nonlinear function, usually expressed in even dimensions in terms of hypergeometric functions or combinations of hypergeometric functions. It's a highly nonlinear function of the scaling dimension delta of the operator that runs in the intermediate channel. So you have equations of this form that you would like to solve, and a consistent answer, consistent set of data is a set of data of C's and deltas that satisfy this equation at all values of Z and Z bar. So these are functional relations. This is pretty constraining, but it's also very complicated. We have an infinite set of equations for an infinite set of unknowns. And we need to decide how to deal with all this complexity. We need to deal, for example, with functional dependence on Z and Z bar. If you want, we can compute an infinite number of Taylor coefficients, send all of them to 0. Also, you compute a different 4-point function, you get different information. So let's discuss two alternatives here. The first alternative, briefly, just to remind you, is the standard numerical conformal bootstrap approach, which has been very, very successful, initiated by a very nice paper in 2008 by Ratazzi, Ryzhkov, Tony, and Vitsy. And the other approach is the so-called in the class of truncation methods, which will be more relevant for what I will discuss and fits more with the previous slides. So for definiteness, let's discuss a specific 4-point function. We take a single 4-point function. We're going to discuss that. You could also consider simultaneously different 4-point functions. And then, of course, the game you're playing in this case is more constraining, and it's also possible to do. Okay, so the first approach is basically a very clever way to go around the complicated problem of solving an equation, an infinite set of equations for an infinite set of unknowns. You make some blind assumptions, and then you derive some rigorous bounds, typically for some low-lying safety data. And this is the modern numerical conformal bootstrap approach. What are the pros of this approach? First of all, you get rigorous bounds. It's a little bit like the variational method in quantum mechanics. You use a test function to find the ground state energy. Maybe your test function is not that great, but nonetheless, you get a rigorous bound on the exact energy of the ground state. The cons is that if you make blind assumptions, then it's hard. I mean, you land somewhere, you get a bound between allowed and not allowed regions, and sometimes you get cusps or islands if you do simultaneous multiple correlation functions. And then that focuses on a particular theory, and maybe you're interested in this theory, maybe you're not. So if you're interested in a very specific theory, say QCD in the conformal window, this approach has been quite hard to implement to get information about that particular theory. And typically also with generic assumptions, you get rigorous results only for a few low-lying CFT data, and you would like to have more. However, let me open a parenthesis here. Once you are on the boundary of the allowed and not allowed region, you can use a very nice method called the extremal functional method, which is not a rigorous method, but gives you access to many, many CFT data. This is something people have been exploiting. Okay, so this is the traditional approach, approach 1, but I want to emphasize here that this is not what I want to do. Okay, what I want to do is try something else. In fact, I want to try something which is more along the lines of the original bootstrap idea by Ferrara, Grilogato, and Polyakov, or more recently by Gliozzi and Lee. So what I want to do is take these equations here, assume a particular truncation, and actively try to solve the truncated system of equations. As we will discuss in a moment, this is not actually a system of equations because you have truncated, and since you truncated, you can no longer satisfy them exactly, but you want to define an error and you want to minimize that error. So why do we use this? Why focus on this approach? Clearly, this approach is much more dirty and much more complicated, and it's not going to be rigorous. So it looks like a big, bad idea. But on the other hand, you sort of open Pandora's box and you look inside, and now you have the opportunity to try different things or try to basically look inside the allowed regions behind the generic numerical conformal bootstrap bounds, which the other approach has hard time doing. So our main hope, to summarize it here, end goal is to achieve a guided exploration, possibly using machine learning methods, or maybe there is some other method, to achieve a guided exploration of theories of interest inside the generic numerical conformal bootstrap bounds. So viewed in this form, this problem now is, so if you think about your cost function, which is the error that you're making by using a truncation and trying to minimize that, that is now a non-linear, non-convex, large-scale optimization problem. Okay, so first comment here, notice how this is different from the first approach. The first approach uses extensively two facts. The fact that, where are my equations here, uses the fact that the OPE square coefficients here appear linearly and uses a lot of linear programming and semi-definite programming methods, and also uses heavily the fact that the unitarity. In other words, that these coefficients here appear with definite signs. So this approach that I'm now trying to use actually gets access to the full nonlinear structure of the crossing equations. And obviously, this is a harder problem. There is also a slight difference in point of view from point of view of Gliozzi and Lee, especially Gliozzi in 2013, who also introduced the crossing equations and tried to solve them. There, the idea was that you make a truncation, and in some cases, you're lucky. You use 5 operators in the truncation, so it's very drastic, or even 10, and you get pretty good numbers. So the idea was that in some cases, you will be lucky, a few operators will do the job, and then you get, this is a cheap way to get very useful information. Our point of view here is we don't want to be necessarily in such a lucky situation. We want to see if you want the generic situation or do multiple correlation functions where necessarily we will have to accumulate or take into account lots of operators. So we want to have the technical ability or develop the technical ability to treat this as a large-scale optimization problem. And usually when you do that, sometimes, well, most of the times, deterministic methods, search methods are not very useful because they get stuck in local minima. So that is something that favors stochastic methods. Okay, so that's the general idea. That's precisely what we want to do. So now let me set and the key steps of the exact exercise in a conformal bootstrap that we want to undertake. So you give me a 4-point function, and you write down the generic conformal block expansion. And then in order to write down something concrete, I need to specify a truncation of the spectrum. So I need to assume that, say, in spin 0, in the intermediate channel, I will write down 10 operators. At spin 1, I will write 5 operators. At spin 2, I will write 15 operators, whatever. I need to write something. I need to allow for specific operators to appear there in order to write down something concretely. The more operators you include, the more, if you want, complete your search is going to be. Clearly, this is a tricky point. If you want, this is the blessing and the curse of this approach. The blessing is that you start having access to lots of data. The cursing is that it's not completely clear always how to use the truncation. The general thing we're trying to implement here is the following. We're interested in specific theories, as I said in the beginning. So you choose your theory, you try to understand that theory. So the idea is to pick the truncation or the spectrum that you are using, using all available information to you. So if you know something about the theory in a perturbative regime, use that to inform the truncation. If you have symmetries in the problem, for example, if you have supersymmetry and some operators are protected and you know the exact scaling dimensions or some other datum you know exactly, implement that in the crossing equation and use it so that the sets is not completely arbitrary, so that you limit the difficulty of looking in a high dimensional space in blind. Use all available information to guide, to write down a problem that has less solutions and it incorporates already the information that you know. And I will give an explicit example of this in the second part of the talk. Now, the second thing you need to do is basically quantify what you mean by error. As I said, is there a question?
Yes.
Yes.
So, there's this manifestly crossing symmetric techniques that are coming up now.
Yes.
Do you have any idea whether your methods can be combined with those to gain more insight?
I don't, but these are all things that I'm watching very closely, precisely, or any results from the analytic functional bootstrap that could be used to make this work better. This is a very good question. So as I will emphasize in a moment, once you start doing this, there are many things you can combine, you need to make lots of choices of how to do things, and none of them is obvious, and you can just, that's why this is so experimental at the moment.
Thanks.
Yeah, sorry, I don't have a definite answer. It's definitely very interesting to try that.
Yeah, thanks.
Yeah, I was looking at these methods the other day, by the way. Yeah. Anyway, so the second thing you need to do is to formulate a semi-positive definite nonlinear functional of the CFT data that quantifies the error that you're doing. So basically, you take the left-hand side of your equation and you act with this functional, nonlinear functional, and you want it to be something which is a semi-positive definite. You want it to vanish and satisfy exactly the crossing equations when the number of when the truncation becomes infinite, when you incorporate all possible operators. Okay, so this is for us, again, in the language that is useful in machine learning, this is going to be the cost function that expresses the violation of crossing equations. And let me give an example. Again, this is an example related to the previous question. This is an example of a point where I have to make a choice. So if you look at the right-hand side, one possible way to view this is, this is a function of z and z bar, the points in the z-plane, the cross-ratio space where you evaluate these equations. You can say, okay, they have to be satisfied at all points of z and z bar, or the error has to be small at all points of z and z bar. Let me evaluate them at nz points, typically a larger number than the number of unknowns that you have, so that this is an over-constrained system, and build a vector of all of these numbers. Okay, let me call it E. Or, as people more usually do in the numerical conformal bootstrap approach, let me take nz Taylor expansion terms around the crossing symmetric, usually the crossing symmetric point, z equals z bar equals 1/2. And build an nz dimensional vector with these coefficients. Then we can define one of the obvious things that you can do to define a cost function is basically take the Euclidean norm of this function. But clearly, this is not a unique choice. And sometimes another choice may be useful. So you have to play around. If you do it in any of these ways, also, it may be useful to think if you want to weigh different points or different regions of the z-plane in different ways. In other words, make a norm here which is weighted differently at different z-points. That's another option that you have. And it's not clear which one you should, is going to work better. The third step is you want to minimize this to find the optimal CFT data in truncated space. in the truncated space of the safety data. In general, this process requires searches in high-dimensional continuous spaces, hence the large-scale optimization problem. And typically, this is so if you think about the cost function as a potential, basically, this is a very complicated landscape with many local minima. And even worse, sometimes you may not be interested in the global minimum. And again, an example of this will appear in the specific application I will make in a moment. Okay, so you need to decide on all sorts of different things. The first general thing you need to decide is which large-scale optimization problem algorithm you're going to use. There are many existing options, from deterministic ones to stochastic ones. And most of them, they don't have any machine learning component, although people are trying to improve standard algorithms using machine learning. There you'll find papers where people try all sorts of different ideas. So on stochastic methods, you can use Monte Carlo or a related method, which is simulated annealing, or evolutionary methods like differential evolution or particle swarm methods, where you have something called swarm intelligence, etc., etc. Now, what we tried to do in this paper in 2021 is something atypical in this context. We decided, for reasons that I'm going to explain, to use a reinforcement learning algorithm to do the search. So that's the first thing you need to decide. The second thing to decide is the following. So you made the choice of algorithm, and now you need to run this algorithm. But as I said, the landscape of minima is very complicated. So you need to decide how you're going to run the algorithm. First of all, if you're using a stochastic algorithm, every time you run it, you're going to get a slightly different result. So you need to run it many times. So it's good to parallelize your algorithm and run thousands of copies on a cluster, so thousands parallel copies on a cluster, and that improves exploration. Then you can also build heat maps. I will show you examples where you see, where stochastically where the algorithm wants to go. Then you need to decide, am I interested in the global minimum? Am I interested in some particular local minimum? Am I interested? Typically, what happens is that there is a basin of attraction around it. It's very spiky, so there are lots and lots of minima. So you may decide that you want to explore all these minima, which is a very hard exercise, or you may decide that what you're interested in is basically identify these macroscopic basins of attraction, and then you get an error if you want the size of this basin, but you don't care about all the microscopics of this landscape. So in the last paper, we have focused on identifying microscopic basins of attraction, and this reinforcement learning algorithm that we're using seems to be good at doing that. Okay, so let me talk a little bit about this reinforcement learning algorithm. So yes.
Before you do that,
yes.
The process you're solving it by is you're taking the FO sum over FO equation, and you're trying to solve equals 0 equation, and you're trying to solve that equation for the coefficients of the various operator product expansion.
Right. So we have an equation like this in the exact problem. Here it is, right? And we don't know the Cs, these are the unknowns, and also the scaling dimensions delta for the operators that appear in the intermediate channel, right? In the S channel and the T channel. So we have a bunch of operators. We assume that, so many operators appear for spin 0, so many operators appear for spin 1, etc., etc. And we don't know their scaling dimensions, and we don't know the OP square the corresponding OP square coefficient. So these are the unknowns. In the Cs, the problem is linear. In the deltas, it's highly nonlinear. Okay. Now, once I truncate, this is no longer a set of exact equations that I'm trying to satisfy. Instead, I have an error function, right, or a cost function, which is positive definite, and I'm trying to find C's and deltas that minimize that cost function.
Okay.
Is it clear?
That is G of this entire thing.
Exactly, exactly. That is right. Exactly. I'm trying to minimize this.
You're trying to minimize that. Okay. Okay.
Right. Okay. Very good. Thank you. Okay. So what about let me tell you about reinforcement learning. First of all, before I talk about this, think about how generically the stochastic algorithms work. There is a predetermined strategy. So basically you make random choices, and You have the space of unknown data, and you go around in this landscape, and you try to minimize your cost function, but you do this randomly. Now, how do you jump from one state to another? Well, you have a fixed strategy. You say, every time I'm here, I will make a random jump with some particular prefixed distribution on another point. I will, collect this or not collect this, depending on my algorithm. Or in the particle swarm, you have many particles running at the same time. And in the middle, they also communicate and, they move around. But you have a fixed strategy on how you do the search. Now, what we found very interesting in this reinforcement learning algorithm setup is that this is something that operates in the general context of the so-called Markov decision processes. So instead of going from one state to another randomly, which is like a Markov process, now you have an agent on top of that. And every time, so you have states and you have actions. So you have an agent that once it's in a state, it needs to decide with some stochastic policy or deterministic policy, what's the next step to make. So in other words, the thing that was previously completely fixed, like your, some probability distribution that tells you how you move around, this is something that will be now, that can be now dynamical. And it's called the policy of how you choose the actions. So this whole context here is, the main elements of this whole context here is what people call Markov decision processes. There is an agent, there is an environment, there are states, there are actions. You also have a reward, and then you have a probability of going from one state to another given a particular action, which is, and the decision part has to do with how you pick the action once you are in a particular state. Okay, so there are algorithms that learn in this way. So the typical, so the algorithm that we use is called the soft-Actor-Critic algorithm, and it, in very rough words, it works in the following way. You have an agent, makes a random action, communicates with the environment gives back feedback. So as I will say, the environment for us is basically a state is, a value for the unknown CFT data. A reward is, for example, this function G, the cost function. So you make a choice and the environment communicates back and tells you how good your choice is. At the same time, the agent behaves like if you want, like a conscious thing. It has a memory, it has a brain, it has a memory, and it stores the previous choices. So it stores a number of the past choices and uses them as experience to make future educated guesses. So in the third step, you update the policy. Depending on how well you did, you may want to improve the way you choose your action, change the way you choose your actions, you update your policy, and then you run again. Okay. Now, yes, please.
How is the goodness of the choice? What determines the goodness of the choice here?
It's how, if the cost function is small or bad at the first level. I will quantify it a little bit more now.
Okay. So
okay, but it's basically how well you did. Did you jump in a region where the reward is, sorry, not the reward here, the reward is something else. We want to maximize the reward. Think of it as 1 over the cost function, okay? If the cost function is small, right, you are in a region of interest, right? You found something that looks like a local minimum. You want to maybe stay there, right?
Yeah.
Okay. Okay, now where does the machine learning part come in into this game? So you might think, okay, so what are machine learning? The basic component of machine learning are neural networks, right? Neural networks are function approximators. Basically, they approximate functions. So maybe the thing you want to approximate here is, the vector of unknowns that you have, which for us, again, I repeat, are scaling dimensions, unknown scaling dimensions, and corresponding OP square coefficients, okay? So maybe you want to build a network whose output are the CFT data, right? So this is not how this works, okay? The main disadvantage in trying to do that is that, you know, as the search becomes higher and higher dimensional, so you have more and more unknowns, that network will be growing, so it wouldn't scale very well. Okay. Instead, this works in a different way. It employs machine learning in a different way. There are, roughly speaking, two neural networks here. One is trying to estimate the policy. What is the policy? If you are in a state, it's a probability distribution because this is a stochastic policy. So it's a probability distribution. Once you are in a particular state, okay, it tells you what is the probability distribution of choosing that particular action. So there is a neural network, fixed neural network with fixed size, independent of how large your search is, that tries to estimate the current policy. Okay. There is another neural network here which estimates, once you took an action and you find yourself in a particular state, you compute the reward, but also you can estimate something that in reinforcement learning is called the value function. It could be the state value function or the state action value function. The details do not matter here. Roughly speaking, this is a function that tells you if you're in a particular state, and if you use, say, the optimal policy, what will be your expected reward in the future? How well you will do if you continued using your optimal policy as you understand it at the moment. That's called the value function. So you use a second neural network, again of fixed size, to estimate these value functions. Depending on how good this value function is, you update the other neural network that computes the policy. Okay, so if you want, these are neural networks inside the brain of the agent, which work together with a memory buffer to help the agent make, as time goes on and on, to make better, more educated guesses. Instead of moving around randomly with a prefixed strategy, it starts learning as it builds experience on where are the good regions and where are the bad regions. So this is the feature that we found very attractive. We thought, you know, maybe this is going to help us scale the problem better. Okay.
So it's a dynamical neural network.
Sorry, say it again.
It's a dynamical neural network, and a neural network which keeps evolving with each
site.
It
gets updated. Yeah, you have a dynamic policy, right? You get these neural networks and they get updated all the time, and you know, they try to optimize.
Yeah.
So if you want, there are all sorts of optimizations that are happening together at the same time. We have the overall optimization that we're trying to achieve in the space of CFT data. But then at every step, we have to optimize also these neural networks or update them as we go along. Okay, and for those optimizations, we use standard methods from neural network technology, like the ADAM method, etc. Okay. Okay, so we use the soft-Actor-Critic algorithm that implements, which is quite popular in robotics, in fact, where the emphasis was on control tasks. It is a nice algorithm. It has the following desirable features. First of all, it works with continuous variables, which is what we want to do here. The actor and the critic are basically these two neural networks. The actor is the policy neural network. The critic is the value neural network. And soft here is another interesting feature. Instead of trying to minimize or maximize the expected reward, you add in the reward or in the cost function, which is related to the cost function, you add to the reward an entropy functional. So now instead of trying to maximize just the reward, the algorithm is set up in such a way that it tries to maximize both the reward and the entropy. And that turns out to make the algorithm more robust. So when they compared it with other algorithms in the context of robotics, these people here, they found that this way of doing things was much more robust and much more efficient. So we focused on this algorithm.
These are similar to GANs, right?
Yeah, exactly. There are all sorts of similarities. That's right. But this is in the context, the GANs are in the context of supervised algorithms, and this is in the context of reinforcement learning algorithms.
In the sense that even GANs are the similar actor-critic, one which kind of does the thing, and the other is kind of always trying to it right. I mean, in a sense, it's
Right.
yeah.
Exactly. Adversarial.
Adversarial, yeah.
Yeah, exactly. And here I'm trying to give the general rough idea of these algorithms. There are different versions of these algorithms, and and you could also try all of them in our context and see if one of them, which doesn't work very well in robotics, works well in this problem. So again, many choices. But again, to reiterate here, the thing that we really like, we found very cool, is that you do the search using it, in the context of dynamical Markov decision processes, which doesn't seem to be, a very well explored subject in the context of large-scale optimization problems. So we thought that it would be cool to try. Okay, so here is the dictionary between reinforcement learning and physics. The environment for us are the crossing equations. The action is to choose a value for the unknown CFT data. A state is, well, you take a particular value, you find a particular value for the individual crossing equations. The reward, as I will say, mentioned in the next slide, or the cost function is the violation of the crossing equations, and the reward is we're going to choose it as the inverse of the cost function. So we want the reward to increase when the cost function decreases. The specific way we chose to do things and compute that cost function is to do a z-sampling along the lines of a previous paper from 2016. So we evaluate the crossing equations in particular values of on the z-plane, on the plane of cross ratios. You can take a large number of these sampling. So typically we have the set that I'm going to show you is a set which is 80 dimensional, roughly 100 dimensional. We took NZ to be of the order of 200. Everything in our algorithm is pre-evaluated. So it doesn't run, it's not evaluated again and again inside the loop. And so it doesn't cost you anything to put a large number of Z points here if you want. Now, what is the reward? The reward, we took the cost function to be the norm, and the reward the inverse of the norm, and we try to minimize the cost function or the violation of the crossing equations, or in other words, maximize R. Our code, our current code, which has been which is public in GitHub, so you can run it for yourselves, is completely automated, and so it can be used to do parallel runs on a cluster. And the code is, we call it Bootstrap. It's called the Bootstrap for Bootstrap Stochastic Optimizer. It's publicly available in GitHub, as I said. At the moment, it incorporates only the SAC algorithm, soft-Actor-Critic, but soon it will also have options for other stochastic optimizers like particle swarm, etc. So you can choose the stochastic optimizer that you like and apply it in the CFT that you like. Good. So let me go into the second part. Are there any questions?
Yeah, so is the strategy going to be that you devise an equation for the vector, which for the dynamics of the vector with each cycle as it changes, so that if you have a sort of a Schrodinger's equation for say a Hilbert space vector, then you can kind of solve, if you can devise a sort of a Schrodinger equation for the Hilbert space vector, then you can kind of solve that equation to get the precise dynamics of that vector and see whether it kind of settles down somewhere or something like that. Is that the strategy you are going to use? No.
No, it's not that, but maybe there's something in what you're saying that can be explored. No, the strategy is what I described. Basically, we use the reinforcement or the generic stochastic optimizer. We make random choices or almost random choices as we, in the search space, which is the space of unknown CFT data. And we try to find the region where the cost function gets minimized. So it's a repeated guessing game. Where you make guesses again and again and again. You try to guess in which direction of the search space you have a minimum or you have a Bayesian of attraction.
Yeah. Okay.
So this is the typical way all the stochastic algorithms work.
Okay.
The only difference is that we're not using a predetermined strategy. We're using reinforcement learning algorithms to, as we go along, to improve the policy of how we choose the next state. That's the difference. Okay, so in 2021, previous August, we wrote a paper where we basically outlined what we wanted to do, introduced the algorithm, and we thought that, we need to calibrate things. It was not at all obvious at all. When we started this a year and a half ago, it wasn't at all obvious to us that, it's going to work. It's, if you, especially the truncation methods are very, very tricky in the conformal bootstrap program. They have all sorts of difficulties that are well known to people who work on the subject. So it wasn't clear to us, if we do these truncated equations, we do a blind search or a general search, are we going to find something that we can identify? So we thought that it's a good idea to test in a situation where we know lots of analytic solutions, and 2D CFTs are certainly such a testing ground, because we have many analytically known conformal field theories. Also, in closed analytic forms, all the global spinning conformal blocks. We did the exercise there using only the global part of the Virasoro symmetry. So we didn't use Virasoro symmetry at all, the special features of 2 dimensions, so that everything could be directly be generalized to higher dimensions. Some of the simple tests we performed is to see if we can locate minimal models. If you went around the neighborhood and you searched around the neighborhood where the minimal models were, you identified them. So as an optimization algorithm, it was working. We were not using at this stage lots of operators, so the truncations were pretty small, like of order or 10 operators, for example, or 5 operators. Which was comparable to what other people had done with different methods in the context of truncation methods in the past. And we performed one of the most interesting examples here was to try to identify the 2D S1 boson CFT, so the free scalar with a target NS1. And what this is interesting because this is a cheap example of a one-dimensional conformal manifold. So usual numerical conformal bootstrap searches find it hard to work with conformal manifolds. And we wanted to test in a case where there is a conformal manifold. And when we picked, in a quite educated way, the truncation, and we let it run, to our surprise, basically, the algorithm identified the data of the free 2D S1 CFT, and that got us excited. The numbers compared to the analytic ones were not, extreme accuracy, like to the 5th, 6th digit or whatever, but it was clearly identifying the right theory. The results reported in that paper were based on single runs on a laptop. And since then, as I said, we have improved the algorithm a lot. It runs in parallel in clusters, etc. And again, we used a low number of operators there. So these were essentially 30-dimensional, including both scaling dimension, OP square coefficients, 30-dimensional, 40-dimensional searches. And this doesn't constitute a large-scale optimization problem, which in our eyes will be something which has of the order of 1,000 operators, a few thousand operators. Okay, so now let me go to the last part. I have, I think, about 10 minutes or so, and I'll tell you about the recent thing that we did, which is the 6D 2.0 bootstrap. So we said, let's try to apply this technology in a problem which is much more difficult, one where basically we don't know anything. We know very few things. So the 6D 2.0 bootstrap is one of the most demanding cases of the superconformal bootstrap. There's no Lagrangian in this theory. We only have information from the large C limit, where we have ADS-CFT, we have ADS-7, process 4, and we also have information, some information about protected data from the correspondence with the 2D chiral algebra. I'm referring to the story of Beam, Rastelli, and Van Ries from 2014. So in 2015, Beam, Lemos, Rastelli, and Van Ries applied the standard numerical superconformal bootstrap approach to this in this context. by studying the 4-point function of superconformal primaries in the energy momentum multiplet and produced some very interesting results. In particular, produced rigorous bounds on the central charge C, and bounds on 3 OP squared coefficients of protected operators, and bounds on scaling dimensions OP squared coefficients on 3 non-protected operators. Now, again, appreciate that in this context, where we have very few tools to attack the theory, anything that is unprotected is basically in the darkness. We don't know anything about it. Also, more recently, last year, Lemos, Van Ries, and Zhao used an iteration scheme, a non-rigorous method, based on the OP inversion formula to obtain non-rigorous curve for CFT data as a function of the central charge C. And they published plots of 12 CFT data on the leading edge trajectory. Now, in all of the studies, we know that in the 2D CFTs, there are 2 series of theories. I'm ignoring the E here, which is special, the A series and the D series. And in all of these approaches, you couldn't distinguish where the A series is, where the D series is. Basically, if you have with a generic numerical conformal bootstrap bounds, you get a bound, and then below that, in the allowed region, you cannot say anything about it. And the expectation is that both the A series and the D series are inside the allowed region, not on the boundary. So you cannot say anything. And also in this non-rigorous method with the OP inversion formula, they produced a single curve by doing iteratively the OP inversion formula, produced a single curve. And it's not clear where this corresponds to. So they also mention it as an open problem, whether they could identify the A and the D series by running appropriately or by finding different fixed points of the iterative scheme they were using. Okay, so let me move towards our results. Again, a little of notation. The superconformal primaries are labeled by these quantum numbers, the scaling dimension, 2 eigenvalues for the Cartans of the SO5 R symmetry, and then for the SO6, we use 3 eigenvalues for the rotations in the 3 different planes, H1, H2, and H3. And we also know what long and short multiplets can appear. They have been, completely classified, L, A, B, C, D. What we're interested in is the energy momentum multiplet. So this is the multiplet that appears in our 4-point function. We take the superconformal primary, which is a scalar, in the traceless metric representation of the SO5R. Okay, so this is the 4-point function we want to analyze. We also know the superconformal selection rules. We know when we take D20 and D20, we know that these multiplets can appear on the right-hand side of the OP. You see here that not all the protected multiplets appear, only the B, D, and the longs L. And for the short multiplets, we know the scaling dimensions because they are protected, but we don't know all of the OP squared coefficients. We know a part of the OP squared coefficients with these D20s, and the ones that we know are the ones circled here in red. And these OP squared coefficients can be fixed using the correspondence with the 2D chiral algebra. This is something that Van Ries, Rastelli, and collaborators did in their previous papers. So what are the unknown data for us? The OP squared coefficients of this protected multiplet, the D40 and the B02s, and the scaling dimensions and OP squared coefficients of the longs, where, as I said, we basically know nothing. So these guys did a very nice exercise, analytic exercise, where they took all the information we know from the chiral algebra, they incorporated it into the general crossing equations, and they ended up with a compact crossing equation at the end, which incorporates all the known data. So this is the crossing equation that we are trying to solve now using our approach. So in this function C here, which is crossing symmetric, you have 3 contributions. The 2 contributions in red are fixed in terms of the known chiral algebra data. So you know them, you don't need to vary with respect to any unknown here. All the unknown data are in this function AU and include scaling dimensions for longs and OP squared coefficients, and also OP squared coefficients for the D40 and B02. Okay. So in the exercise that we did in the last paper, basically we try to answer the following questions. question. If we go to the supergravity limit, where we have a rough idea of the theory, well, we have the idea, the large C idea of the theory from supergravity. If we use the non-spectrum there, which is a generalized free field spectrum, what will happen? What will our algorithm discover if we take the spectrum, build the truncation based on that spectrum, the generalized free field spectrum, and then start changing C adiabatically? What kind of minima or extrema are we going to discover? How did we fix the truncation? We take, again, the generalized free field spectrum. The red dots are the protected data, and the blue dots are operators in long multiplets. This, you can view this as basically they are double trace operators. So we truncated it at, say, for the long multiplets up to spin 12 and up to spin 18 for the short multiplets, the unknown short multiplets. And in order to test whether this is a good truncation in the large C limit, we used this truncation, we implemented this truncation in the infinite C limit, and we optimized using our algorithm. And indeed, our algorithm slightly rearranged the solution away from the analytic values, because we make a truncation, we make an approximation, hence the small displacement, but immediately gave very high reward, which was, a completely atypical reward compared to other rewards we were getting with blind searches. So this convinced us that this is a good starting point as a truncation in the large C limit. But of course, it's not completely obvious, or it's not at all obvious. If you start changing C adiabatically, at what point this truncation breaks down? In other words, when is it a good approximation, when it's not a good approximation? At ICTS, we performed 2 sequential 8-hour runs with 200 agents on the high performance cluster in Queen Mary. And before I actually present you the results, we had to make a choice, right? We needed to ask the following question. Okay, so what does it mean to do an adiabatic search, change C adiabatically? The most obvious thing to do is what I call protocol 1. In other words, you do a run in a particular value of C, you get a mean value and a statistical average and a 1 sigma statistical spread around that average value. So when you change C, you can run the new search around the previous average and see where the code finds the new value. So this is the obvious adiabatic protocol you can explore. That, however, will produce a single curve, and we will be expecting here 2 curves. So in other words, we're not looking for a single optimum here, we're looking for 2 optima. Can we motivate, how can we search for the second optimum? One observation was the following. If we look at one of these data, this one, the red dot here, the lowest one, which is the D04, it's the lowest protected multiplet. The only thing we don't know about this operator is the OPE squared coefficient. So we know that this has to vanish exactly at C equals 25, which is the A1 theory. And we also observe, if we look at the asymptotics, the large C asymptotics of the A curves and the D curves, we notice that the OPE squared, the value of the OPE squared coefficient for the D40 is always smaller for the A series compared to the D series. So that motivated the second protocol, which was the following. Once we did the search, and we got a result at a particular value of C, the program, the algorithm is outputting, the best results, the best 100,000 results, for example, in a big Excel file. You get the 100,000 best results from the 200 parallel runs. So you go there and you look at the values of the D40, and you look for high reward runs that have a comparatively small value of the D40. So in the second protocol, we run the code in the next value of C, by not around the previous statistical average, but around this value that we were identifying in the data set around the highest reward with lowest D40 p-square coefficient. Okay, so let me show you what we produced. So we produced in this way two curves as a function of C for, again, how many data are we varying here? We have 45 operators in total. 10 of them, which are the red ones, are protected, so we don't vary the scaling dimension. So in total, we have 80 unknown CFT data. So we are performing an 80-dimensional continuous search. And we produced, as a function of C, plots or data for 80 CFT data as a function of C, and the reward, the two curves had comparable reward. So here are the results. So this is the protocol 2 result. Let's look at the D40, okay, OP squared coefficient of the D40. The red dashed curve is the numerical, the generic numerical conformal bootstrap bound. And the brown curve is the curve that Van Ries and company obtained using the OP inversion formula. It is below that formula. What we obtained with the protocol 2, where we were going around the lowest D40 p-square coefficient, is something like this. The statistical errors are not huge, and it's very much comparable. It's below the known bounds and very much comparable with the OP inversion formula. Notice that, like with the NP inversion formula result, at C equals 25, we should be getting analytically 0, but we get something around 0.8. So clearly, at this point here, we haven't, with this truncation and these assumptions, we're not getting close to that. But, this is a result which is below the numerical bounds and comparable with the OP inversion approximations, which are completely different. Okay, what about the long multiplet, the leading long multiplet? Sorry, wait 1 second. Again, the D40, this was the protocol 2. The protocol 1, where we were running around the previous average, produced this curve here in the orange, which looks like this. It is above, for most of the values, it is above the numerical bounds. So you look at this and you say, oh, this is a disaster. It doesn't behave very well, this run. But then you think a little bit about it and you notice several things. First of all, one thing that is typical in all the data we got with this protocol is that after the region of, for values of C which are smaller than, well, for C to the minus 1/3, which is larger than 0.15, the statistical errors start increasing, and the quality of the searches becomes harder, becomes worse. You see here, for example, the green dot is a statistical mean, and the purple dot is the best reward. And you see the best reward is some value that was outside the 1 sigma region. So something seems to be happening to these runs, basically after 0.15. Now you ask, okay, if this curve here, which has visibly higher D40 lambda squared compared to the other curve, is the D-series curve, I shouldn't extrapolate it all the way down to C equals 25. I should extrapolate it up to the lower possible value of C that I have in the D-series. It turns out that the lowest value of C for the D-series is basically 676, which corresponds to the value of C to the minus 1/3, which is around here, 0.11. So if I terminate this curve at this point, the violation compared to the known bounds is very small. In fact, the deviation from the known bounds starts becoming significant precisely around this region. And this, as I will show you later, is typical for all the D-series curves that we obtained. If you terminate at this value of C, either you're below the known bounds, or it is the region where you start violating the bounds, which is very suggestive in our opinion. So in that sense, the D-series curves, which at first sight look like the worst ones, I think they are the best curves we obtained in these runs, because they are always within or very close to the known bounds. Okay, so here are the data for the scaling dimension delta, and I'm ending in 2 minutes. These are the data for the first, the lowest lying unprotected multiplet. This is the scaling dimension. You can see what we got with a black curve. The dust curve are the known numerical bounds, numerical conformal bootstrap bounds, and the OP inversion formula is in the brown. It seems we did quite well. And for the, that's the corresponding datum for the D series. Here you see again the thing that I noticed before. You see the violation for this curve starts precisely when the D series is supposed to be ending. For the OP squared coefficient, again, it seemed we did quite well. We're below the numerical bounds and comparable to what people obtained with other methods using the OP inversion formula. And for the D series, again, we're always below the bound. Okay, so let me summarize. This is just a sample of 80 different data, 80 different curves, separately for the A series and the D series, and most of them are new. Predictions for most of the data that we produced haven't appeared before. Keep in mind that as we go closer and as we increase the scaling dimensions and go closer and closer to the upper bound of our truncation, the data become less reliable, and you can also see this in the statistical spread, it grows. So some of these data violate the bootstrap bounds. Others behave very well, like the lowest ones that I showed to you. Some do better or worse than the OP inversion formula. And the approach, I think the important thing is that the approach identified two distinct high reward curves, which could be the A and the D series curve. So something that we couldn't do with other methods, rigorous methods, seems to be doable in this approach. What are the good features? The good features is that we have been increasing the number of CFT data. We're still quite low. 80-dimensional or 100-dimensional searches are not yet large-scale optimization problems, but we are increasing. And we, as I said, we are exploring behind the generic bounds in the allowed regions. What are the bad? It's not yet accurate enough. Obviously, this particular truncation is not enough. The algorithm has not converged yet. So we need to try larger truncations. And one can incorporate more operators. We believe 100 operators instead of 45 are already doable with the current implementation that we have published in GitHub. So we are planning on exploring this, but anyone who's interested can try for themselves. And please, take a look at Bootstrap and see if you can use it in any way that you see useful. So let me stop here, and I'm open for discussion and questions that you have. I have many more plots, so if you want to, I can also show you more plots if you want. Okay, thank you very much.
Yeah, let's thank Vasilis for a great talk. Any questions?
So in the space of the OP data, I'm just trying to reiterate my question that I asked before. I'm trying to sharpen the argument that I was giving before. In the space of the OP data, each solution, for instance, suppose the OP data take value. Sorry. Suppose the OP data take different values, and for each different value, that course, I mean, if you kind of say that each OP datum is an axis, is like an axis.
Yes, exactly.
Then for different values of the OP data, the vector which corresponds to the data spans a certain space, spans the space of the possible values of the OP data. And that space is like a manifold, right? In the space of
exactly.
Now the tip of that vector, it's like a vector in Hilbert space. I mean, even if you consider the entire set of.
It's not exactly a vector in a Hilbert space because in
not a Hilbert space, but I say configuration space. I mean, not exactly
in configuration space. Yeah, you don't have the linearity because you cannot add them and etc.
Maybe, yeah, possibly you don't have
Because it's a non-linear problem.
It's a non-linear problem. But
That's right.
I mean, I was just wondering whether so now the equation that you have, the FO sum over FO equation, is precisely the equation for this vector.
Exactly.
Yeah.
But it's a truncated version that we're using, right? It's not the actual equation, which has an infinite number of unknowns.
Yeah, see, even when you have even if you have the Schrodinger's equation, say suppose you're considering the Schrodinger's equation. The Schrodinger's equation is what? I mean, the psi of x at different points, the different x's at different points, they represent different vectors, right? In the Hilbert space. I mean, if you consider delta, the various delta.
Well, you can think of them as different components in the space representation.
In the space, the various points are various components in the space.
Exactly.
So in a similar fashion, the various. I mean, and that space is infinite dimensional, right?
Right.
Space is infinite dimensional. So I mean. But that, I mean, the vector there, the Hilbert space vector there has a very simple equation, the Schrodinger's equation. It's a differential equation. I was wondering whether you can cast the FO equation into sort of a integral differential equation and solve it numerically.
Well, here I have an algebraic equation, right? I don't have, or a functional equation. I don't have a differential equation.
No, you have an equation in terms of F and O. And in those F and O, the Z's are involved, right? The various.
Right, and I have to satisfy it for all values of Z, right? That's right, yes.
The
I don't have derivatives, okay, yes.
You don't have derivatives, but you have,
right, that's right.
You have certain equation.
Right, exactly.
The various parameters.
Exactly, right.
Yeah, so they are kind of algebraic, so they're kind of algebraic equations, but see, the equation is in terms of F and O. So I was just wondering if you reframe or recast the equation in terms of the parameter in the OP data, in terms of the OP data, then whether that becomes sort of a differential or an integral differential equation. I don't know.
It's not. It's an algebraic equation.
Okay, so if it's an algebraic equation, then it's even better.
Yeah, exactly. It's even better. That's right.
Easier to solve.
Yeah, easier, but it's not easy.
Yeah, I mean, yeah. So for you have an infinite set of equations, right? Do you have an infinite set?
Right, exactly. I have an infinite set of equations. That's right.
Yeah.
So and I take all of these equations, right? And basically I try to see they are not equations because I have truncated, and I evaluate them and I try to minimize them in order to satisfy them as almost equations. And I have lots of them. As I said, I was using nz equals 200. So I have 200 equations in what I was running.
Yeah.
I have 200 almost equations that I'm trying to, whose error I'm trying to minimize in a search space with 80 unknown data, continuous data. And
I was just wondering whether this manifold viewpoint gives any insight into the thing, because each of those equations.
Somdata, could we continue the discussion perhaps offline if there are other questions? And so, thanks.
Are there other questions?
No, but also this is a seminar, and there are. I mean, we also have to let the speaker go. I mean, it's been about 1.5 hours.
Okay. So, any question you have, we can also discuss afterwards or whatever. I mean,
right.
Available. So.
Right. I actually had a question, Vasilis. So this value of C that you start with, this really large value of C, what is that?
Let's value of C. Sorry, what is the?
So you said you start somewhere near the Sugra limit, which is C infinity.
Yes.
You come down to C equal 25. So what's the numerical value that you use to approximate the supergravity limit?
Oh, C equals infinity.
100.
No, C equals infinity. because in our equations, I run a little bit fast. So when I write this equation here, this function in particular is completely known as a function of z and z bar, and it includes c. In particular, it includes 1 over c. So we're playing with 1 over c. So taking c infinity is just setting this 1 over c parameter to 0.
You don't have to do that numerically.
Yeah, exactly. It's
okay.
not that I have to make an approximation. And then we took points here. You can see these are the values of C. So this is infinity, then 8,748, 288, 145, 1,445, etc., etc.
I see. So you start at 0. That's the
exactly. I start at 0 for 1 over C, and I start increasing it.
I see. Okay. Yeah. Great. Thanks. So you seem to have a lot of data points for C away from infinity, but
yeah, exactly.
Because that's probably where you're interested in.
Yeah, it wasn't clear. Here things do not vary a lot. They start varying around here, but it wasn't clear how adiabatically we should go. So I was taking, enough points. So all of these runs were like 2 8-hour runs, so 16-hour runs, two sets of them. And, for every run, I had 200 parallel agents. So the cluster didn't give me the opportunity to start all the 200 agents at the same time. So, it started, the first 50, and then it had to wait, or the first 100, and then it had to wait, which means that all these runs took about a month. But not because, just for practical reasons, not because the runs themselves were very expensive, but because we had restrictions on the cluster.
And at any point in the middle, you were not sure whether you'll get something interesting at the end. It was,
yeah,
you had to wait till then.
Yeah, it wasn't clear, and you were looking at the data. I saw you here the lowest lying data that behaved quite well. Other data, do not behave as well. Here is an example. You see, we went above the bound here, right? So it's obvious that this thing hasn't converged, and we have to put more operations and see how better it behaves. But another thing I wanted to emphasize here is that it's also interesting to think, which comes back also a little bit to the previous discussion. We're used to, in the standard numerical conformal bootstrap approach, right? We isolate, 1 or 2 data, and then we get these very nice rigorous bounds on them, and we do precision stuff with a single datum, etc. So we focus on that single datum. But here, because of the nature of the approach, we're trying to get not just a single datum, but 100 data at the same time, or 200 data at the same time. So we should really think of them as a single point in a 200-dimensional continuous space. So if I wanted to quantify what is the error compared to bounds, right? So I will have to plot all these bounds as some hypercone or whatever in this 100-dimensional space, and then see where my point there lies. So it could violate one. So if it violates a little bit 1 or 2, 3 bounds, but is good for all the rest, then that's not it's less of a problem than violating all of them, for example. So you have to see all of them at once, so which is a slightly different viewpoint.
Thanks.
If I may, can I just make a small point?
Yes.
Yeah. So the thing is, each of these equations, they delineate a codimension 1 plane in the whole space, right?
Yes.
Right. So
yeah, they give you one relation, right? If you satisfy them as equations.
Yeah. So and the solution solution lies at the intersection of all these codimensions.
Of all of them, right? Yeah, right. Or if you want, you get lots and lots of minima, because you're looking for minima.
Yeah,
but they are discrete.
Yeah, they're discrete, but
exactly.
if you don't look for minima, but if you look for equals 0, I mean, if you look for the right hand side to be equals 0, then each of them delineate a codimension 1 plane. Each of the equations delineate a codimension 1 plane.
Right.
Just as a linear equation in a 2-dimensional space delineates a line. So and the solution will just be the point which ultimately becomes the intersection point of all these codimension markers. I don't know whether this has any.
Yeah, if you could view them as equations, but you cannot
Yeah.
view them as equations, right?
You don't view them as equations?
No, because I have truncated, right? So I don't expect to find data that satisfy all of them, and it's an over-constrained problem.
Yeah. But
Now,
just
if you took them, if I took, say I have 80 unknown data, right? And I take 80 equations, right?
Yeah.
Then presumably you can satisfy them.
Yeah.
As equations.
Yeah.
The answer will depend on which Z points you picked, or which Taylor expansion coefficients you pick. So it will depend on, but then it's more along the lines that you're mentioning. You will get some equations, and you can try to satisfy them at the same time.
Yeah, true. But if you have infinite if you have infinite dimensional space, it becomes much harder. And
Exactly.
Your approach is better. Yeah. I get the point.
Yeah.
All right. Any other questions for Vasilis? Well, if not, let's thank the speaker again for a really great talk and for fielding all the questions. Thanks, Vasilis.
Thank you very much. It was a pleasure.
Have a great
Bye,
day.
everybody.
Bye.
Bye. Bye, Surat.
See you guys. Bye. Thank you for the talk.
Bye. Bye.